This lesson is on using calculus to determine the concavity of a graph on specific intervals. The concavity of the graph comes from the second derivative of the function, much like the increasing or decreasing feature of a graph comes from the first derivative. The first thing we're going to talk about is the definition of concavity and what a function looks like if it is concave down or concave up on an interval. Concavity, as you will learn in your pre-calculus course, is the curvature of the graph, whether it's kind of curving upward or downward. If a function is concave up on an interval, it's U-shaped, shaped like a U, like a regular parabola, or bow-like. You can think of it if you poured water into it, the water would stay inside of it, it would hold water. The formal definition of concave up is that all the tangent lines lie below the graph. So if you were to draw tangent lines here, they all lie below the graph. They are not above the graph. So if it's concave up, it looks like a U. Up begins with a U, it looks like a U. Concave down is just the opposite. N-shaped or dome-like, upside down U, like a parabola with a negative x squared coefficient. You can think if you poured water on top of it, the water would roll off of it or run off the side. And again, the formal definition is just the opposite. The tangent lines all lie on the top, above the graph. So if you drew your tangent lines, they're all on the top. All your tangent lines have to be above the graph. So a graph is considered concave up or concave down. Some vocabulary or terms or concepts you need to understand with concavity. Concavity is determined by the second derivative of the function. Like I said, we're now going to use calculus to determine what a function looks like. In the last lesson we learned about increasing or decreasing, relative min, relative max. Now we're learning about between those relative extrema, and as it's increasing or decreasing, is it concave up or concave down on those intervals? A point of inflection. A point of inflection is a point on the graph where the graph changes concavity. It changes from concave up to concave down, or from concave down to concave up. Points of inflection can only occur where the second derivative is either 0 or undefined. That's the only place a point of inflection can occur, where the second derivative is 0 or the second derivative is undefined. Similar to relative min and relative max occurring where the first derivative is 0 or undefined, points of inflection can only occur where the second derivative is 0 or undefined. But also, just like critical numbers, just because the second derivative is 0 or undefined doesn't mean it has to be a point of inflection. It's just a possible point of inflection. So in order to determine concavity, you want to find all your possible points of inflection. Well, your possible points of inflection occur where the second derivative is equal to 0 or undefined. So your first step, find all possible points of inflection. You derive it twice, then set that second derivative equal to 0, or find where that second derivative is undefined. Once you do that, you have your possible points of inflection, 2, 3, 4, maybe 1, depending on the function. You're going to set up a sign chart just like we did with first derivative test. You have your critical numbers for first derivative test, where here you have your possible points of inflection and you list them. And then you're going to test a value in each interval, but make sure you test that value in the second derivative to determine if it's concave up or concave down. Just like you plug numbers back into the first derivative to see if the function was increasing or decreasing on the interval, you plug the numbers back into the second derivative to see if the function is concave up or concave down on that interval. And again, very similar to increasing or decreasing. Same ideas, except first derivative determines whether the function is going up or going down. Second derivative determines whether the function is concaved up or concave down. Here's some examples of some points of inflection. They're not as easy to see on a graph as a relative extrema is. Relative extrema is at the top and the bottom. A point of inflection takes a little bit of time to get used to identifying where that happens. So you see here, this first graph. If I cut this off like this, everywhere to the left you see a smile or a U shape. It's concaved up. Everywhere to the right, it's concave down. So the point of inflection doesn't occur if the the top and the bottom. It kind of occurs in the middle from where you're going concave up to concave down. So that red dot would be a point of inflection there. Here you got a point of inflection at a horizontal tangent. It looks like part of an x cubed graph. On the left side, you're concave down. On the right side, you're concave up. So your point of inflection comes there where it looks like you have a horizontal tangent. So you actually have a critical number there also. And here would be an example where your point of inflection happens where the second derivative is undefined. You have a vertical tangent line here, so the first derivative is even undefined. So you're concave up from here, you're concave down once you pass that point. Now here's a picture of a graph, and you're going to be asked to identify where the points of inflection occur on that graph. So if you look, it starts off coming from the left as concave up. It's a slight curve, but it is definitely curved up. In the middle here, turns into an upside down U, concave down, and then back on the right side, it curves back up again. So I'm going to kind of trace this graph in there, and it looks like somewhere around those two x values is where the point of inflection occurs. Before you're concave up, after you're concave down, and then you're back to concave up again. So your points of inflection would be right here and right there. Here's an example of a problem. I picked a problem that was very simple to derive and set equal to 0, but the idea is still the same, no matter how complicated the equation is. Okay? The idea is still the same. To find concavity, you want to find the second derivative and find out where that second derivative equals 0 or is undefined. And then between, before, and after those points, each of those intervals will have the same concavity. The only time it can change is at one of these points, or one of these x values, where the second derivative equals 0. So f of x equals x to the fourth minus 4x cubed. Derive it once, 4x cubed minus 12x squared. Derive it again to get your second derivative, 12x squared minus 24x. Set that equal to 0, so you're going to factor. Always factor to set things equal to 0. I have 12x in each term. I'm left with an x minus 2. So my possible points of inflection are x equals 0 and x equals 2. I don't know if they are points of inflection yet, but the only place from negative infinity to positive infinity, the entire graph, the only place this can change concavity is when x is 0 and when x is 2. So we're going to go second derivative, 12x squared minus 24x. We know x equals 0 and x equals 2 are our only possible points of inflection. So we're going to set up a sign chart there. Number line exactly the same as what we did yesterday with the increasing or decreasing. And you test a point in the second derivative. So I pick negative 1. I get 12 minus negative 24, 12 plus 24. Doesn't matter if the value is there or not. It matters if it's positive or negative. 12 plus 24, definitely a positive number. Pick a number between 0 and 2, you go with 1. 12 minus 24, definitely negative. I'm negative on that interval. The function is negative on that interval. And then you go back after 2, plug in 3. 12 times 9 is 108. Minus 24 times 3, which is 72. Definitely positive. So we're positive here. So I'm concave up on this interval. Concave down on this interval. Concave up on this interval. You must actually write it out and show the open intervals. You will concave up from negative infinity to 0 and from 2 to positive infinity. And make sure you leave these as open intervals again. At 0 and at 2, you're neither concave up nor concave down because your second derivative is 0 at those x values. And then you're concave down between 0 and 2 again with your open interval. As you look, this function is concave up, concave down, concave up. That means that both at 0 and at x equals 2, the function changes concavity. Therefore, both 0 and 2 are your x coordinates of your point of inflection. So in order to find the actual point of inflection, you need an x and a y value. So you go back to the original function. To get your y value, you go to the original function. 0 to the 4 is minus 4 times 0. You get 0, 0. would be 1 point of inflection. And then you plug in 2, 2, 4, 8, 16, minus 32, you get a negative 16. So, points of inflection are at 0, 0, and 2, negative 16. Cut you out a little picture of this graph here. At 0, 0, you see the function is coming down, concave up to the left, and it's concave down to the right. So 0, 0 does show as a point of inflection on the graph. And then 2, negative 16 at x equals 2 down here. This is scaled by 5, so you can see this does happen down to negative 16. Straight down from 2. So before here you're concave down, after here you're concave up, and it stays concaved up as it continues towards infinity. So finding points of inflection is very similar to finding critical numbers, using critical numbers to find relative extremity. Finally, there's something called the second derivative test. Just like the first derivative test, the second derivative test is used to find relative extrema, relative maximum, or relative minimum. So, if the derivative of a function is 0 at a specific x value, if you know the first derivative is 0, or if the first derivative is undefined also, then you could have a relative extrema there, a relative max or min. You don't have to, but you could. You can use the second derivative to find that extrema. And the idea is, if the first derivative is 0, you know that you have a horizontal tangent. So if you have a horizontal tangent, and you know what the second derivative is, the value of the second derivative, you can use that to see what the concavity at that point is. So if the first derivative is 0, the second derivative is greater than 0, it's a positive number, that means the function is concave up there. So if you have a function that's concaved up with a horizontal tangent, the second derivative tells us, the second derivative test tells us, that that gives you a relative minimum. It's concaved up, so it's U-shaped, horizontal tangent, so it's at the bottom of that U, must be a relative minimum. And the opposite over here, the first derivative is still 0, the second derivative is now less than 0, so you're concave down. The function's concave down, and it has a horizontal tangent, it must be a relative maximum. The second derivative test is kind of counterintuitive if you see it real quick. Second derivative is positive, you have a relative minimum. Second derivative is negative, you have a relative maximum. But if you focus on what the second derivative means, a negative second derivative means it's concave down, so that means it's shaped like an upside down U. Well, then the point's at the top, so it does make sense. So make sure you walk yourself through what does it mean, what does the graph look like.